Hello, I'm Laura Cassidy from the American Chemical Society. Welcome to this news briefing from the ACS Fall 2019 National Meeting in San Diego. We're joined today by Dr. Bob Howell from Central Michigan University. He's studying flame retardants from plants. Dr. Howell?
Thank you. To begin, I'd like to say a few words about polymeric materials. They're ubiquitous in modern society. They're everywhere. In fact, we wouldn't have the quality of life that we do were it not for polymeric materials. And you can see that simply by looking around this room. The floor covering, the chair covering, the tabletop, the computer housing, they're everywhere. Clothing. These materials are derived from petroleum. They are carbon-hydrogen compounds. That is, they look like gasoline, and so they're quite flammable. And so for most applications, they must be flame retardant. And the development of flame retardants, development of polymeric materials has come about largely since the war. But even in ancient Egypt and Rome, people worried about cellulosics, particularly theater curtains, which they tried to flame retard by treating with alum and vinegar. But as polymeric materials developed, the necessity for flame retardants became more and more apparent. And traditionally, there have been two classes of organic compounds that have been used most commonly. The first of these were organohalogen compounds, particularly organobromine compounds. Because they were inexpensive, they were readily available, and they worked well. And the other was organophosphorus compounds. They were a bit more expensive, but also were very good flame retardants. I would like to just say a few words about how materials burn. If you have a polymer surface and it begins to be heated, you get to the temperature at which polymer degradation occurs. That liberates small molecules, fuel fragments, which get into the air, mixes with oxygen. If you're at a temperature above the ignition temperature, combustion starts. And we see that as a flame, which provides heat and light. The heat feeds back to the polymer, enhances degradation, enhances the feed flow, and the flame grows. So there are two avenues that one could use to prevent this. One would be to form a char layer on the surface of the degrading polymer. So would provide insulation from the flame, so you would diminish the formation of fuel fragments and the flame would be starved. The other would be to put something into the polymer which would degrade at the decomposition temperature of the polymer to form materials which would scavenge the combustion propagating radicals. Both approaches have worked. Traditionally, the organohalogens have been gas phase active that liberate hydrogen bromide, which quenches the flame propagating radicals and quenches the flame. A problem that has become apparent with the organohalogen compounds is that when you throw items away, you don't keep your dishpan forever, you throw it in the landfill, and these things leach from the item, and organisms attempt to degrade them, they attempt to eat them, but they are not able to because they're stable. And so larger organisms eat these and so on to work their way up the food chain so that ultimately gets into the human diet. In certain areas of the world, there's a significant level of these things in the fatty tissue of the human population. Now, fortunately, they're organic soluble, so they tend to stay in the fatty tissue, but it's a real problem. Several diseases have been associated with them. And so you need an alternative, and the focus has been on organophosphorus compounds. Organophosphorus compounds, depending on the structure, as we've been able to demonstrate in this work, function either in the solid phase. If there's a lot of oxygen of phosphorus, you get liberation of phosphorus acids, which promote cross-linking and char formation, and that prevents heat feedback. Alternatively, if you have phosphorus compounds with little oxygenation of phosphorus, say a phosphonate, That liberates PO radical to the gas phase, and it behaves very much like the organohalogen compounds. In our particular case, we've been interested in utilizing plant precursors for generating phosphorus flame retardants for a couple reasons. One is that these materials are common to nature. Most organisms can use them as a food source. You probably know that phosphorus is an essential element for both plant and animal life. In fact, Procter & Gamble is one of the largest users of phosphoric acid. And so that's a plus. The other plus is that they're not based on petroleum, so they're independent of fluctuations in petrochemical prices. And ultimately, we're going to run out of petroleum. And so we've looked at a number of particular sources for these things. In this particular case, we were using Gallic Acid, which is very common in a huge number of plants. All of you have experienced it. If you rake leaves off your lawn in the fall, the brown color is due to Gallic Acid. And the other is 3,5-dihydroxybenzoic acid. It's also available in a wide variety of plants, but primarily from buckwheat. You probably know that buckwheat flour used to be very common in the U.S., but after the advent of nitrogen fertilizers, wheat displaced it, and so we now have predominantly wheat flour, but it's still prized in Japan for noodles and in the southeastern U.S. for pancakes. And so this particular presentation focuses on those two materials.
Thank you, Dr. Howell. Are there any questions? Please state your name and affiliation before asking your question.
Hi, so it's Kath O'Driscoll from Chemistry and Industry magazine. I'm interested in the availability of these precursor compounds, gallic acid and the hydroxybenzoic compound from plants. I mean, maybe the gallic acid is common and might be easily sourced, but certainly buckwheat isn't that common. And I'm wondering, there are lots of concerns about competition with food plants. And so how easy is it actually going to be to source those starting materials?
Well, gallic acid's very easy. It's widely extracted from a large number of sources. It's commercially available in huge quantity at reasonable price. You're right about taking those things from food sources, and we have in the past made some materials from plant oils, and we've typically used castor oil because it is not a plant oil. But with respect to the dihydroxybenzoic acid, there are lots of sources. It's just that it's available at high concentration in buckwheat. That's why that accounts for the antioxidant properties of buckwheat.
Okay, thank you. And in terms of the properties of these organophosphorus compounds that you make, do they, when you actually use them as retardants, do they interfere with the properties of the, say, the polymer at all, or the material with which they're coated or applied?
Yes, very good point. In fact, if they interfere with mechanical properties, then they're probably not useful. But at the level you need these, it's usually 5 to 20% by weight in the polymer. They typically have a very little impact on the physical properties. And that's something we always check. I mean, everyone does. I mean, they simply wouldn't function as a flame retardant if they ruin the properties of the material. You may know that for some applications, there are inorganic materials that are used, but you have to use 50, 60, 70%. And so the polymer properties are gone. So you can use them for things like paper coating, but not in a place where you need integrity, where you need mechanical strength. So these don't hamper that.
Thank you.
Katrina Kramer, Chemistry World. I was wondering, to make the actual flame retardants from the plant extracts, what kind of synthesis or procedure is involved?
Okay, the synthesis is very straightforward. It's reasonably simple, and that's another requirement. If these things are ever to be commercial, the chemistry has to be accessible. And so in this particular case, you simply are converting the hydroxyls on these things to esters, phosphorus esters. You do that with a phosphoryl chloride, and either the phosphoryl chlorides are commercially available or the phosphite from which you can derive the phosphoryl chloride are readily available at low cost.
So it's like a two-step procedure, more or less? Or
Well, no, one step.
One step, okay.
You make the phosphoryl chloride in situ. So one pot, one step.
Thank you. And actually, one more question. The flame retardants you get out, are they chemically identical to some that are on the market, or are they slightly different?
They're different than anything on the market in that they are derived from natural sources. There is interest commercially in developing these kinds of things, and a couple companies are working in that direction, but as yet, there are no commercial flame retardants that are plant-based. So we're hopeful.
Thank you.
Katie Cottingham, American Chemical Society. So have you done toxicology tests yet? Do you know how they react to humans, or what the effects are?
We haven't done toxicology testing on these materials, but there have been toxicology on similar kinds of things. So for two reasons, we think they'll probably be fine. One is that the precursors are non-toxic. So all we're doing is making a phosphorus ester. In particular, phosphates are generally non-toxic. In fact, they're food components. We think we're fine. But you're right, we will have to do that at some point down the line if they go forward. You probably are aware that the toxicity of phosphorus compounds is very much dependent upon the particular structure. You can go all the way from nerve agents, right, to food additives. But in the great middle ground, the phosphorus esters, there's very little toxicity. And there have been a couple of really nice studies to demonstrate that, and I'm sure there'll be more as more of these materials become available.
I was just interested, it's Kath O'Driscoll from Chemistry and Industry. I was just interested, I know there's been a lot of discussion about the availability of phosphorus itself and limitations of the amount of phosphorus, and I'm just wondering, if it's needed for something like flame retardants, is that not going to be a bit of a drain?
Very good question. I mean, the amount of phosphorus is limited. And in particular in the U.S., our supplies are being rapidly diminished. There's still a fair amount in the Middle East and Russia, so there is a fair amount around, but we have not been very good stewards. What we do is we throw it away, and there's a huge amount of phosphorus that goes through wastewater treatment plants, every city in the country, every day. And ultimately, it's likely that we will try to recover that. I mean, it wouldn't be that difficult to do, but yes, that's a problem. Now, fortunately, although lots of flame retardants are used, compared to other materials, it's pretty small. And so the amount of phosphorus required for that purpose is not nearly what's required for food. And so while it's an issue we've thought about, it's not so pressing at the moment, but down the line, obviously we have to do better.
Okay, thank you.
I have a question. How does the flame retardancy of these plant-derived compounds compare to, say, organohalogens if you're comparing equal amounts added to a product?
Well, in general, they're quite comparable. These particular materials, one of them in particular is very good. The dopoester of Gallic Acid, the limited oxygen index is 27. UL94 rating is V0, so it's a very good material. In general, you can get as good behavior from phosphorus compounds of the right structure as you can any organobromine compound. What made the organobromine compounds so popular was that they were readily obtained at reasonably low cost, and they worked well. If you, on an elemental basis, phosphorus is more expensive than bromine, right? And so, unless there's a good reason, you might not do that.
Are there any other questions? All right, thank you, Dr. Howell. The archived version of this session will soon be posted at bit.ly/ACS 2019 San Diego. Please join us for our next press conference at 10:30 a.m. today on producing protein batteries for safer, environmentally friendly power storage. Thank you.